Hi, it's time for another math easy solution. Turn to discuss further into the applied project, how fast does a tank drain video series, and now go over question 4, but I'm only going to go over the basically an introduction or overview of question 4, and in later videos I'll go over parts A and B. Basically, if you haven't seen my first 3 questions, make sure to watch those as I go over recap on this project, but I'm not going to do that. I'm not going to go over too much on the recap in today's video, but instead I'm going to jump into question 4. So now question 4 is basically stating that, well, not all water tanks are shaped like cylinders. In my first 3 questions I went over basic cylinders, tanks like this, and then determined the drainage formulas, height of the water, etc. From this type of shape, this simple shape like that. But not all of them are like that, and instead, question 4 for the introduction, I'll go over basically what happens if the shape is just a general shape, so not a cylinder, or it could be a cylinder, but just a general shape. So let's suppose a tank has a cross-sectional area A of h at height h, then the volume of water up to height h is, and I'll draw that in a bit. But so let's just look at just a general shape. Let's take one that looks something like this. So here's a general shape of a tank. Actually, I'll draw a bit better here. Let's just say it's flat at the bottom there. So you have a general shape like that. Yeah, so this is a tank like that, and then let's say we have this, and let's draw a random cross section inside. Assume this is water inside here. So let's say this is it's filled up to here, and the height of this water is, well, let's draw an axis right here. Let's draw a height axis. So at this point we have height h, and then inside here this is the water level. Again, assume it's all 3D, just a random shape like that, and this is the area, the cross-sectional area A of h. Yeah, so this is a cross-sectional area, and basically recap on integrals and volumes as I did in my earlier videos. If you were to take a cross-section, I mean, if you took, let's say, a length across it here, we'll call this dh, so a thin slice here, etc. Sum this up to infinity. As this goes infinitely small, we get a volume of, and I'm not going to go over too much into that. Basically, if you wanted to learn more on integrals and volumes, make sure to watch my earlier videos on that. So this would be integral from 0 to h here. So the volume of water all the way up to this height, this water level here, is just going to be h, 0 to h, and then the integral of the cross section a, and then but here instead of writing h, we're going to write u because of this h right there, just to not get confused, and then du right here again because of this. So this is just change in variable simply because of this h is the same. We're plugging in h inside there. So I'll just write note change of variable. That doesn't matter here. It's note change in variable, but it doesn't matter what it is. It could be x, y, z, etc. But the fact that we chose the limit from 0 to h here, we just want to differentiate which one it is. In other words, if this was u, we could just put these h and then etc. So this is the volume of this shape right here, and again, you could just look at a small section, ah times dh, sum it up to infinity. It's this infinitely small, and we get an integral based on this Riemann sums and etc. other principles of integration. So now that we have the volume of this shape, and it's a general shape, so it's just a general integral, and now from the fundamental theorem of calculus, recall that is just, well, the derivative dv over dh of an integral. So this is going to be, well, the derivative of the volume in terms of h. It's going to be d over dh of this integral 0 to h, and then au du, and then from the fundamental theorem of calculus, the derivative of an integral is just this integrand here. So this equals 2A of H. Again, U is just a placeholder. Change in variable, I'll write placeholder here. So that's all it is, doesn't matter what it is. So this is just A of H when you plug in that. So that is what the rate change of volume is, just the cross-sectional area. And thus it follows what with the chain rule, if we were to take the derivative dV over dt, so the rate change of the volume, in terms of time, so especially when we're dealing with drainage, and again dV over dt, as I went over my first 3 videos, basically trying to derive dV over dt. This is from Torricelli's law, but also derive it by using the formula for the volume. So we look at the volume here, and now that we've found dV over dH, apply chain rule. So dV over dt is going to be equal to, well, by chain rule, because it's all assuming it's a function of time, which it is when you're draining water out of the tank. This is going to be dV over dH times it by dH over dt. So the height's going down with time. Same with volume. It's all related. So we have to apply chain rule like this. Derivative of volume is derivative of volume in terms of height, and then multiply derivative of h in terms of time. And then this equals 2 because we have this dV over dH is that. So this equals to A over H dH over dt. Yeah, so this is what we have now. I'll circle this. And then what happens to now our Torricelli's law, that becomes, well, let's just look at it again and write it down. So we have dV over dt equals to negative A square root 2 GH. So if we look at that, this is the original Torricelli's law, dV over dt. This is negative A square root 2 GH. Again, where A is the area of the outlet hole, or whatever it is where water's draining out. G is gravity. So now that we have this, we can just plug in this inside. That's our dV over dt. So what we end up getting is this differential equation, A of H, or the cross-sectional area of the water, dH over dt is equal to negative A square root 2GH, and this is the formula that we will use for further parts of this question. Alright, so now that I went over this formula, and then in next videos I'll go over, next video or two, depending how long those take, I'll go over part A and B, where the part A says suppose a tank has the shape of a sphere. So we look at a sphere, radius 2 meters, initially half full, and if the radius is a circular hole or the outlet hole is 1 centimeters, and then there's gravity, assume it's 10 meters per second squared, is rounded up from the typical 9.81. And then it says show that H satisfies this differential equation over here. And again, it looks similar to this. This is, just plug it into, this is basically, it looks just very similar to this. So just show that the values are these for this specific example. And then part B says how long will it take for the water to drain completely. And again, I'll go over these in the next video or two based on how long it takes. Just because, those are pretty in-depth examples here. And this part here, I wanted to go over an introduction first. It's to show how we can write, the volume of just a general shape, and then throw that into Torricelli's law. And then from here, we will be able to solve questions such as these: how long will water take to drain of a sphere, for example, and not just a cylinder. And again, we would go from here and then go from here, etc. Anyways, that's all for today. Hopefully you'll learn from this pretty interesting video on just a general shape of a tank as opposed to the typical cylinder that I went over in my earlier videos. Anyways, all for today. Hopefully you'll learn. Like always, you can download these exact notes in the link below. Thanks for watching, and stay tuned for another Math Easy solution.